Last hour, we discussed independence and conditional independence. And we said that two events that are independent conditioned on, two events A and B conditioned on another event C, may or may not remain independent when the conditioning is lifted. Okay? This next example shows that conditioning may affect independence. Okay? The example is, assume A and B are independent, but A intersection B intersection another event C is empty. Okay? So if we're told that the event C occurred, then are A and B independent now? Okay? Drawing a Venn diagram can be a very easy way of exhibiting a counterexample showing that A and B may not be independent. So here's a counterexample. Events A and B, so let this be event A, let this be event B. Okay. They have a non-empty intersection. Okay, if they had an empty intersection, then we would know that they are dependent. Right? Disjoint means dependent. So assume, so suppose A and B are independent. Okay? Let the event C be like this. Let this be the event C. Okay? C has a non-empty intersection with both A and B, but not with the intersection of A and B. Okay? So let's compute the probability of A intersection B given C. What is that? This is 0. Why? Because if C is given, now C is the new universe. And in this new universe, A and B cannot both happen at the same time. Okay, so this is different from the probability of A given C times probability of B given C. These are different from 0, at least whenever both of these are different from 0, the left-hand side is not equal to the right-hand side. So this is a counterexample showing that events that are independent may not remain independent when conditioned on something else. Okay. Any questions? Okay. So let's now do an example to illustrate conditional independence more. Okay. Let's take two unfair coins, A and B. Unfair coins, meaning the probability of heads and tails are not 1/2. In fact, if you pick coin A, the probability of heads is 0.9. On the other hand, if you pick coin B, the probability of heads is 0.1. So coin A is more likely to produce heads, and coin B is more likely to produce tails. Okay? But once we pick coin A, if we keep tossing it, each toss is independent of each other, and each toss results in a head with probability 0.9 independently of all others. Okay? That's the question setup. Now, here is a randomized algorithm for coin tossing. I choose either coin with equal probability. So I first toss a fair coin. Depending on the result of the fair coin toss, I pick either coin A or coin B. Okay? And I continue the rest of the experiment with that coin that I picked. Okay. Question is, once you know it is coin A, are future tosses independent of each other? Yes. In fact, by definition of the problem. Once you pick coin A, each toss is independent. Once you know it is coin A, each toss independently results in heads with probability 0.9. Now, here's an interesting question. If you don't know which coin it is, are future tosses independent of each other?
Yes.
Let's think. Maybe we should make that question a little more precise. So to make things precise, I would like to compute the probabilities. First, let's compute the probability that the fifth toss is at tails. Okay? The probability that the fifth toss is tails. I don't know which coin I picked. Remember, I start the experiment by tossing a coin, fair coin, or with equally likely, I'm equally likely to pick coin A or coin B. If I pick coin A, then I get heads or tails. The probability of heads is 0.9. The probability of tails is 0.1. And in further trials are going independently with the same probabilities. If I pick coin B, on the other hand, heads has probability 0.1 and tails have probability 0.9, etc. Okay? So let's compute the probability in general without conditioning on which coin I've picked. What is the probability that the fifth toss of this, fifth toss of the coin in this experiment is tails? Does it matter whether I consider the fifth or the sixth or the first? No. How can I compute this? I can apply the total probability theorem. Remember, we talked about, when we first talked about the total probability theorem, I told you that it would be very useful in the future. So here is an example of where it becomes very useful. So I can break this into an event and its complement. Let the event be pick coin A. Okay. This is the probability that the fifth toss is tails given I picked coin A times the probability of picking coin A plus the probability that the fifth toss is tails given I picked coin B times the probability of picking coin B. Because coin A and coin B are the only two possibilities. So they are the complements of each other. So let's compute this. What is this probability? Given coin A, it's tails with probability 0.1. 0.1 times, what's the probability of picking coin A? 1/2. Plus, fifth toss, tails given coin B, 0.9 times 1/2. So what do I get? Surprise, 0.5. I had two unfair coins. I converted them to one fair coin. It's like magic, right? Randomized algorithms work like magic. Okay? This is the randomized algorithm. Choose either coin with equal probability. Okay? This random strategy or policy creates a fair coin out of two unfair coins. Okay, except it's not that simple. If you can observe the past tosses of the coin, if you can observe the results, the outcomes of the past tosses, you start making an inference about the future. In fact, you infer something about which you can infer something about which coin you have, and then in the rest of the time you could use the probabilities for that coin. So here's what I mean. Let's compute the probability that the fifth toss is tails, given that the first 4 tosses all resulted in tails. So, what do you think? First of all, before attempting the problem, what would you think the answer is? Approximately. If all first 4 tosses resulted in tails, then maybe it's quite likely that you have coin B in your hands, right? In that case, the fifth toss is quite likely to result in a tail too. Okay, let's compute this, make it precise. The probability that the fifth is tails, given that all first 4 are tails, is the probability that the fifth is tails and all first 4 are tails. Remember, I'm using the definition of conditional probability divided by the probability that all first 4 are tails. Now, what is this event? The first 4 are tails and the fifth is tails. This is all first 5 tosses are tails. Now, again, use total probability theorem. Probability 5 tails, I'm going to shorten this. 5 tails given coin A times 1/2, the probability of picking coin A, plus the probability of getting all 5 tails given I have coin B times the probability of having coin B, divided by the probability of the first 4 all being T. Okay, so the probability of 4 T's given coin A times 1/2 plus the probability of 4 T's given coin B times 1/2. What is the result? 5 tails given coin A. If I have coin A, then at each toss, independently, I get tails with probability 0.1. Huh? Yes. So 0.1 raised to the power 5 is the probability of getting 5 heads in a row times 1/2 plus, if I have coin B, each toss results in tails with probability 0.9. 5 tails in a row is 0.9 raised to the power 5 times 1/2 divided by, do the same in the denominator, this time for 4 tails in a row. 0.5 to the 4 times 1/2 plus 0.9 to the 4 times 1/2. Okay, the 1/2s cancel, and well, these terms are much smaller than these terms. So it's not hard to show that the result is around 0.9. Of course, it's a little less than 0.9, but it's very close to 0.9. So since the 2 coins have very different probabilities, in particular coin A is very unlikely to result in tails. If you have observed 4 tails in a row, this makes it highly unlikely that you have coin A, and highly probable that you have coin B, which makes the conditional probability of the 5th toss being tails close to 0.9. In fact, the more tails you observe, the closer to 0.9 it gets, and eventually it converges to 0.9. Any questions? So basically, going back to where we came from, if we don't know which coin is given to us, the past carries information. The past outcomes carry information. They carry information about which coin it may be. Okay? So successive tosses are not independent of each other unconditionally. Okay? But conditionally, they are independent. Right? So let's write this again. Probability that the probability of getting 5 tails in a row, given that I got 4 tails in a row and I have coin A, is what? If I have coin A, if I know that I have coin A, the past observations don't matter anymore because coin A has a fixed probability of giving me tails, and that is 0.1. But as we computed over here, unconditionally, the probability of getting 5 tails in a row, given that I got 4 tails in a row, is approximately 0.9. Okay? So, okay, any questions? Yes, please. Tosses are independent of each other when we condition on a particular coin because we assumed that when you toss coin A, every toss results in heads with probability 0.9 independently of other tosses. Okay? So when we are given that it's coin A, nothing can change this probability anymore. That probability is fixed. Okay, when we're not given that it's coin A, then this carries information. Okay? So this is an example showing that things that are conditionally independent may become dependent when the conditioning is removed. Okay? So think about this example if it confuses you at this point. I think this is a pretty good example. This also is very related to information theory and estimation. Okay? So these ideas are, these are ideas that lie underneath a lot of interesting theories. Okay. Let's move on. We define independence for 2 events, okay? We can also define independence for more than 2 events. Independence of a collection of events means that information on some of the events, a group of the events, tells us nothing about the others, okay? So, precisely speaking, suppose events AI, A1, A2, A3 up to AN are independent. This is true if and only if the probability of the intersection of AIs on any subset S of the set of indices 1 through N breaks up into a product P of AI. P of AI, I again taking values in the set S. Okay, so in particular, if S is 2, then there is only one subset with more than one element. That is 1, 2 itself. So the A1 and A2 are independent if and only if the probability of A1 intersection A2 is probability of A1 times probability of A2. Let's think about it for 3 sets. When for 3 sets, n is 3, how many conditions do we need to check? Let's see. The set 1, 2, 3, how many subsets does it have? 8 subsets. But one of the subsets is empty. That makes 7. 3 of the subsets are size 1 only. That leaves 4. We need to check 4 conditions. Okay? N equals 3, A1, A2, A3, independent as a group, if and only if the probability of A1 intersection A2 is P of A1 times P of A2. And P of A1 intersection A3 is P of A1 times P of A3, and P of A2 intersection A3 is P of A2 times P of A3. One more. What is that? P of A1 intersection A2 intersection A3. P of A1 intersection A2 intersection A3 is P of A1 times P of A2 times P of A3. So these are the 4 conditions that need to be satisfied for the 3 sets A1, A2, A3 to be independent. If only these 3 are satisfied, these imply that the sets are pairwise independent. These are the conditions for pairwise independence. Okay? But for independence as a group, we need all 4 conditions to be satisfied. Okay? So for n equals 4, n equals 4, how many conditions? Excuse me? How many subsets with 2 or more elements? 16 minus 4 minus 1, right? Which is 11. So in general, 2 to the n, 2 to the n, minus n, minus 1 conditions need to be checked and satisfied for n sets to be independent as a group. Okay. So remember, for 2 sets, we said A and B are independent if and only if A and B complement are independent. Now, for general n, the group A1 through AN are independent if any combination of these sets is independent of any other combination. In particular, A5 union A2 intersection A1 union A4 complement. Okay, given A3 union A6 complement must, as a consequence of these conditions, it can be shown that this conditioning drops. Why? Because this is independent of this. Because every individual set is independent of every other individual set. So basically, since they are all independent things, by combining them, you cannot create, by combining a group of them, you cannot create any dependence with another group unless, of course, there are sets in common between the two groups. Okay? So as an exercise, I recommend that you show that this holds. Okay? So show this as exercise. Okay? Pairwise independence, which means satisfying these conditions only pairwise, does not imply independence. Okay? So if you want to confirm independence, checking PAI intersection AJ equals PAI times PAJ for all IJ is not sufficient to confirm independence. For 3 events, again, checking that the probability of the intersection of all 3 breaking up into this product is not enough for confirming independence. Okay? So let's do this example. Consider 2 independent tosses of a fair coin. Okay? A is the event that the first toss is heads. B is the event that the second toss is heads. And C is the event that the first and second toss have the same outcomes. Okay? Are these events pairwise independent? So first toss resulting in heads and first and second resulting in the same outcome. First of all, A and C, are they independent? Let's check. Let's first write down the probabilities. P of A is first toss is heads, 1/2. P of B is 1/2. P of C, I toss 2 coins and I want them to have the same outcome, either heads, heads or tails, tails. What's the probability? 1/2. Okay. Now compute probability of A intersection B. What's that? That's the probability of heads, heads, right? Which is 1/4, because the 2 are independent. A and B are independent. Okay? Why? Because we are considering 2 independent tosses of a fair coin. Okay? P of A times P of B. Okay? What's next? Let's try A and C. This is the probability that the first is heads and the first and second are the same, which is again 1/4. Well, this is equal to P of A times P of C. Okay, so A and C are independent, A and B are independent. Similarly, B and C are the probability of, again, heads, heads, which is 1/4, which is P of B times P of C, independent. Okay. So all 3 events are pairwise independent. Are they independent? We need to check this last condition to see if they are independent. A and B and C. The first toss is heads, the second toss is heads, and the 2 tosses are equal. Well, that is again the probability of the event HH, which is 1/4, which is not equal to P of A times P of B times P of C, which is 1/8. Okay? So this not being satisfied makes us conclude that A, B, and C are not independent as a group. Okay? So what's happening is just by knowing A, or just by knowing B, I don't have full information about C, and in fact it turns out A and C are independent and B and C are independent. But if A and B are both given, then I know for sure whether C happened or not. Okay? So, any questions about this? Okay, here's another one. Consider, again, two independent tosses of a fair coin. Oh, it's the same example, sorry. Let's compute, have we computed these things? P of C, yes, 1/2. P of C intersection A, 1/4. C intersection A intersection B, 1/4. C given B intersection A. Yes. And that being different from P of C shows that C is not independent of A and B. Okay. So here's another quite classic example about network connectivity. As electrical engineers, I'm sure this will seem pretty straightforward to you. Okay, here's the example. In the electrical network, in this figure, each circuit element, so these rectangles show individual circuit elements, okay? Each circuit element is on with probability P, independently of all others. Okay? Now, there's a connection between points A and B if and only if I can find the path from A to B, an uninterrupted path on which I pass through only elements that are on. Okay? What is the probability that there is a connection between points A and B when the elements act randomly like this? So remember, each element is on with probability P independently of all other elements. What is the probability that the network is connected? That is, points A and B are connected. How would you approach this? So, let me maybe repeat, roughly sketch the figure over here. Okay, there's two elements here, one element here, a parallel connection here, and another element here, and two elements in parallel here. Okay, B. And this is A. Let's call this point C. Okay? So, A and B connected if and only if A and C are connected and C and B are connected, right? Okay. So A and B must be connected and B and C must be connected. Are these two events independent? Yes, because this event, A and C being connected, depends on these elements. Let's number them. 1, 2, 3, 4, 5, 6. CB being connected depends on these elements only, 7 and 8. 7 and 8 are independent of 1, 2, 3, 4, 5, 6. Okay? As a group, these 8 elements are independent of each other. So this subset is independent of this subset. Okay, so this must be connected and this must be connected. What is the probability that CB is connected? probability that CB is connected? Well, either element 7 or element 8, because they are connected in parallel. What is the probability that either 7 or 8 is on? It is 1 minus the probability that both of them are off. Right? 1 minus p squared. Right? 1 minus p squared is the probability that 7 and 8 are both off. Okay? So 1 minus that is the probability of CB being connected. So we got this part done. Let's do the first part. Probability of AC. Now, AC is connected if, and only if, at least one of these 3 branches works. Okay, so the probability that it is connected is 1 minus the probability that none of the 3 branches works. Do you agree? Okay, the connection between A and C is off if and only if all these branches are off. Okay. Now, but the branches are independent, right? Yes, because the branches have independent elements. They don't depend on each other. So this probability is the product of top branch is off times the probability that the middle branch is off times the probability that the bottom branch is off. What is the probability that the top branch is off? Right, for the top branch to work, both of these elements have to work because they are series connected. Okay, so if either of them don't work, then they won't. So 1 minus p squared. Okay, because p squared is the probability that that branch is on. What is the probability that the middle branch is off? That's easy. 1 minus p. What is the probability that the bottom branch is off? It's off if either this doesn't work or one of these doesn't work. Or again, let's think negatively again. It's off if it's not on. So 1 minus the probability that it's on. When is it on? It's on, first of all, element 6 has to be operational, which happens with probability p. And 4 and 5 don't have to be both off at the same time, which is 1 minus p squared. So put all these together. 1 minus p squared times 1 minus p times 1 minus p times 1 minus p squared. Okay? And multiply this with this. Okay? Any questions? Let's see. So what are the 2 ideas that we used here? First of all, we used the fact that when a group of elements are all independent, this means the associated events of each element being on are independent as a group. Okay? So because of this, take any subsets, subset like 7 and 8. 7 and 8 is independent of 1 and 2. Any combination of 7 and 8 is independent of any combination of 1, 2, 3, 4, 5, 6, etc. Furthermore, any combination of, for example, 1 and 2, here they are series connected, and 4 and 5 are in parallel in series with 6. No matter what you do with 4, 5, and 6, you cannot create independence with 3, for example. Okay? So this makes life very easy. We can compute the probability that this branch works. Please work this out example again on your own and make sure it's easy for you too. Make sure, computing the probability of an event happening by subtracting from 1 the probability of the complement is, becomes habitual for you too, because sometimes it's very useful. Okay. Next topic is independent trials, but it's a better idea to start that topic at the beginning of next time. So we'll have a full hour to devote to these topics. I'll see you next time.